So let me give this to you here. Suppose you have a symmetric matrix. Suppose you have a symmetric matrix here. Then here are some fun facts. One, A has in real eigenvalues. Counting multiplicity. Let me point out that some of these conditions aren't good enough. What do I mean by that? I mean, if you're symmetric, that happens. Just because that happens doesn't make it symmetric, right? It's sort of, you all are familiar with these kinds of implications, right? Like, for example, if you have a Lexus, you have a car. But just because you have a car doesn't mean you have a Lexus, right? And if I doesn't believe that, you can look at my car, which is a McDonald's dumpster with an engine in it. Let me give you an example of this. This matrix right here has two real eigenvalues counting multiplicity, 1 and 1, right? But it ain't symmetric. Right. Two, the dimension of each eigenspace if E lambda is eigenspace corresponding lambda, then the dimension of E lambda is equal to multiplicity. That is how many times lambda repeats in the root. Number 3, all eigenspaces are mutually orthogonal. That is, if you take a vector v out of one eigenspace and a vector u out of a different eigenspace, they're automatically orthogonal. They sit at right angles to each other, so to speak. And 4, A is orthogonally diagonalizable. And this one is an equivalence in the following sense. If this holds, and if A is orthogonally diagonalizable, it has to be symmetric. So that's a theorem that we had last time. Okay. Let me point out something that will be useful in the last section that we will get to today. One, I think this is kind of interesting, right? And it's not obvious at all. But if you have any symmetric matrix, any one that you could create, a real symmetric square matrix, then all its eigenvalues are real. This is, to me, this is not clear at all. How should this be proved? Well, let's see. Here's a kind of a neat little proof of this. Suppose A is symmetric. That is, suppose A and AT are the same thing. And let's let those. And let's suppose that AX and lambda X are the same thing. For x not zero. So in other words, x is a eigenvector corresponding to eigenvalue of lambda. I want to show that lambda actually has to be a real number. So how would I do that? So let's let x. Okay, so what do I mean by this? Let me point out before I get too carried away with this is at my starting point, I don't know anything about this except that A is a symmetric matrix. So what I mean by that is lambda doesn't necessarily have to be real. It might be complex, right? And the eigenvector doesn't necessarily have to be real. It might have complex entries in it as well. Right? Now, I want us to look at this for a moment. What is true about this? Right? A times x is an n-dimensional vector, real or complex, right? Then you multiply by its transpose. This is a complex number. It is a number. This is a one by one matrix. Everybody okay with that? And that's really all I need to notice here. Because let's suppose, let's call this Q. And I don't know anything, don't know much, but Q is a complex number, right? I'm going to prove that it's a real number. If I take bar means complex conjugate, I'm taking the complex conjugate of that whole thing. Everybody agree with that? And complex conjugate works one at a time. This is actually right. So the conjugate of this whole thing is the conjugate of this, which is back to xt, right? The conjugate of this and the conjugate of this. And you know what? I'm going to not put the hat on the vector. I'm going to leave my vector's house so I don't confuse this. This is regular x. This is complex conjugate. Everybody okay? What's the conjugate of A? It is A because A is a real matrix, right? So this is which is equal to that. How did I make this step? Don't make it too complicated, it's not too fancy. What I said is this matrix is equal to its own transpose. Right? But really, the only thing you need to know about that matrix that I transpose is how big it is. What is the size of this matrix? It's one by one. Right? And so what's the transpose of any one by one matrix? Transpose of a number? The number itself. Right? So that's all. This no big mystery. Everybody okay with that? Now, how do I transpose things? I transpose in the other order. Right? As you saw last time. But what's the transpose of A? It's A. Is a symmetric. And what's the transpose of the transpose? It's X. And what's another name for this? Q. And where did we start? So here, what I've discovered is I have a complex number Q, and it equals its own complex conjugate. what complex numbers are actually equal to their own complex conjugate? The real ones, all the ones that are real, right? And so see if you can now use this to deduce that so as an exercise. I've done this little computation. See if we can use this to use this is real number. I'll give you a hint. What is AX? It's lambda X, right? So run with that. Okay. And finally, I think I want to tell you, and I'm going to give you just kind of a brief little example of spectral decomposition. So there's two kinds of decomposition. We'll talk about, I'm going to just tell you briefly about this so-called spectral decomposition. And then I'm going to talk about singular value decomposition, which is the last section of new material that we have on the syllabus. I'm not going to do that whole section. For the singular value decomposition, and for this one really, I just want you to know kind of how it works. I want you to be able to build it. And I'm going to do an example there of building singular value decomposition, which I may not be able to finish today. We'll do it tomorrow if I can. Suppose where D so D is a diagonal matrix with eigenvalues on the diagonal. P so in other words, let me kind of remind you all, since P is orthogonal, I know what's another way that I could write PDP inverse. Maybe an easier way to find P inverse. PDP transpose, right? That's the cool thing about orthogonal matrices. They're square and their inverse and transpose are the same thing. Right? So let me write this down here. So you have A is P the inverse. So A is a matrix that is orthogonally diagonalizable, so it's symmetric. This is U1, UN, comes this crazy matrix here, diagonally, times the matrix U1 transpose, U2 transpose, UN transpose. That. And this is lambda U1, lambda 1 U1, lambda 2 U2, lambda n UN times U1 transpose with UN transpose. And so if you multiply this out using column row stuff, so A, which is where we started, we're doing this big computation here, you can actually decompose this into a bunch of n by n matrices that look like this. U2 transpose, lambda n, UN transpose. And this is called the spectral decomposition. So let me write this down again, and I'm gonna make some remarks about what this should look like. And then I'll give you kind of a concrete example. So we have A, with lambda 1, U1 transpose, plus lambda 2, U2 transpose, with lambda n, UN transpose. So let me make some notes. Every column in the matrix UI transpose is a multiple of the column UI. So these are singular matrices, right? Well, that is bigger than or equal to 1, or bigger than 1. And 2, we call UI transpose a projection matrix. And I'll show you this. A projection matrix because if X is in Rn, so if you get some vector X in Rn, what does this matrix do to it? Well, U1 or UI transpose acting on X is the orthogonal projection. Into the span of the vector U and I. So let me write down this matrix here. And let's kind of build this thing here. What do I want to do? Let me do this. Okay, so notice this is a symmetric matrix, so I should be able to get an orthogonal diagonalization of this, right? To do this, I first need to find the eigenvalues, the eigenvalues. So this is good practice. So let's look at the determinant of 7 minus x, 2, 4 minus x, which equals x squared minus 11x plus 24. I reckon. Oh, it's looking at me. So I've got 2 eigenvalues, 8 and 3. Okay. Let's see what I get for eigenvector. By the way, here's kind of the hint of what's going to come. Right? It's a 2 by 2 matrix, and I got 2 different eigenvalues. So that means that both my eigenvalues, I don't have to do any of this business with Graham-Schmidt, right? Because the eigenspaces are going to be one dimensional. What spits out of here should be orthogonal. So all I have to do is normalize it. That's kind of cool. So let's look at lambda equal to 8 first. And if I subtract 8 from the diagonal, with -1, 2, 2 minus 4. Notice this row is multiple this row as it should be. Right, so I'm feeling pretty good about that. And an eigenvector for this bet you I get something like 1 minus 2 now. That's not bad here. That equals 3. So this one I subtract 3 from the diagonal, and I get 4, 2, 2, 1. How about that? Another single matrix to be expected. Notice this is multiple of this. Right? So this is really, I can rescale this to 1, 1/2. 3. So I get, let's say 1 minus 1/2. And I'm going to scale this because I hate stupid fractions. 1 minus 2. Now, we're right to want to orthogonally diagonalize this. Somebody tell me. Well, actually, you've got a couple of decisions to make. Somebody tell me what's the diagonal form you want.
8, 3.
Okay, sure, that works. How did he know to pick the 8 first? It doesn't matter, but now something matters. What matters now? Right, now you have got to make it match its appropriate eigen vectors. So in particular, what should the first column of this be of my P?
2, 1.
Good. And my second column, thing I scaled to, that's the same length, I guess it's going to be. And as you get comfortable with this, I mean, guess what? The inverse of this should be its own transpose, right? And looks like, yeah, because notice this one's also symmetric as well, right? And yep, it appears to work. But this is kind of cool because it's an example of matrix squares to itself, and it's not something silly. Remember how earlier in the class I said how many matrices, 2 by 2 matrices square to the identity? And we said, well, there's at least, I think we got at least 4, right? 1, 1 on the diagonal, -1, -1 on the diagonal, -1, 1, 1 minus 1. Here's another one, right? So apparently they're all over the place. Okay, so in our spectral decomposition, what we should get is A is equal to, let me write this down, well, U1 transpose plus lambda 2, U2 transpose. So for us, this would be lambda 1, we did 8 first, so I'll do that. The vector U1, and this should be the vector U2, the columns of this matrix here. This should be 2 over radical 5, 1 over radical 5, and you transpose it, 2 over radical 5, 1 over radical 5. second eigenvalue is 3, and U2, 1 over radical 5 minus 2 over radical 5 times its transpose 1 over radical 5 minus 2 over radical 5. So notice what we're going to be doing is building. Notice this is a 2 by 1, 1 by 2, so this builds me a 2 by 2 matrix. So this comes to now let's see what we get. This is 8 times the 2 by 2 matrix I get. Let's see, that should be 4/5, 2/5 across the top row. And across the bottom row, I should get 2/5, 1/5. Got another 2 by 2 matrix. It should be 1/5 minus 2/5. And then minus 2/5, 4/5. By the way, these matrices should all turn out to be, because what you have is a U times a U transpose. Notice it equals its own transpose. So all these matrices should turn out to be symmetric, and they are. Right? And what happens when you add them up? Let's come full circle on this. This is 32 and 3. It's 35/5, which is 7. This is 16 minus 6 is 10/5. This is 16 minus 6 is 10/5. And this is 8 and 12 is 20/5. Notice that these matrices are singular, right? Because this column is multiple of this one, multiplied by half. This column is multiple of this one, multiplied by -2, right? And check out that statement about it being a projection. You should do a computation with that as well. Okay, any questions on that?
What's the point of finding that?
What's that?
What's the point of finding that?
Because oftentimes when you have physical problems for different eigenvalues, they're very special spaces, right? Because remember what eigenvalues are, that's where the linear transformation only acts like a stretch. And so oftentimes with these kind of matrices, what you're doing is you break the linear transformation up into pieces where it's well behaved, pieces that you want to study. Maybe you don't care about these eigenvalues because they're negative, so you only want to look at these particular subspaces, right? It's kind of a practical thing that you may encounter.
So you can break it up into multiple structures, basically.
What's that now?
You can break up one matrix into multiple structures.
That's right, that's right. And when you decompose, so this will sort of, even though it doesn't directly answer, it might sort of indirectly help. So this sounds like, Courtney, I'll just filling up your time here, or something like that. But what we're going to talk about also, because this is very much why would you do it kind of thing. So what is the singular value? So this is another one where we take a matrix, we break it up into pieces, right? Suppose, here's the cool thing about this, because what we've done so far is, oh, well, if you're a symmetric matrix, then you can orthogonally diagonalize it, right? But you don't just, symmetric matrices, it's not like you encounter them daily on the street, right? It's like somebody from Montana. They're pretty rare out of the population, right? So that seems kind of specialized. And a lot of these things work, maybe they're going to work for singular matrices and verbal matrices. The cool thing about singular value decompositions is we are going to get a singular a way to factor this down into pieces that we get chunks that we can handle easily, no matter what properties the matrix has. In fact, it doesn't even have to be square, right? So here's looking forward. If A is an m by n matrix, any m by n matrix, then can decompose factor A as follows. In this form, so we can break it up into three matrices, and these matrices are like pieces of meat that are easier to chew. We cut it up into simpler pieces. Where U is M by N orthogonal. So you can make M, not only is it invertible, it's orthogonal. B is N by N orthogonal. So my bookends are orthogonal matrices. I've got U, which is orthogonal, so it's transposed. And this is the inverse, if you will. It's transposed to orthogonal. And if you believe me so far, sigma, which I don't really like using that notation, I apologize for it. I just stick with what folks do here. I don't like this notation for this, but anyway. What is the size of sigma? What does it have to be? It has to be the same size as A, right? Because this one is M by M. This one is N by N. And this one is M by N. And so the piece that you need in the middle to make this balance out is M by N. So again, guy in the middle has the same size as the original matrix. But the difference here is I'm bookending it with two different size matrices. They're orthogonal, but if M and N are different, they can't be inverses of each other because you can't even multiply the two bookends together. You can't even multiply them. And okay, anybody want to criticize me on that? Throwing that word around like that. I'll be a critic. Everybody is.
I guess because it's not square, it's not.
That's right. I mean, what do I really mean by diagonal matrices? This is not square. Well, so what I mean by this is it's got a diagonal chunk up here that is, well, if we take the non-zero elements of the diagonal chunk, I didn't need that. Let's read what I said. Where this has n minus r columns, and this has n minus r rows. Where R equals the number of non-zero entries. Let me just kind of draw you a picture of this. Let me give you a couple of examples so that we can, kind of get a feel for it. Let me give you some examples of non-square. I mean, I for sure I know what it means to be diagonal in square matrix, but for example, this would be an example of what we call a diagonal matrix, right? Or you can have one like this. So basically, you start the non-zero entries in the upper corner and just work your way down until you potentially run out of space or you start getting zeros. Right. But here's the thing that is to me is spectacular. It doesn't matter about A. Like I said, it doesn't even have to be square. I can take this matrix and I can flank it by two orthogonal matrices. and make it be sort of the analog of similar, although it's really not, of a diagonal matrix, right? This is kind of cool. You might ask yourself the following question. We know that there are matrices that cannot be diagonalized, right? Say square matrices. In fact, I gave you one over today, 1, 1, 0, 1 can't be diagonalized, right? Orthogonally or otherwise, it can't. So what happens when you do a singular value decomposition of that? So let me, so now that I've put my spoiler alert in, let's try to talk about this. I haven't even told you what a singular value is, but we'll at least get this far. Now, the first thing I notice is somehow I'm going to end up flanking this with orthogonal matrices, right? And the only matrices that I know that are diagonalizable orthogonally are the symmetric matrices. And what do I have? I have A off the streets here. I mean, it's not even square necessarily, so it's certainly probably not symmetric. But can we associate? How would we go about this? Building something. Let's let A I just hand you a thing. I want you to come up with a concrete way. So I just walk up to you and give you a 2x6 matrix. I want you to give me a concrete way of coming up with a square matrix that's symmetric. Given my input, what could I do?
It doesn't have to be the same, right?
No, so it's not going to be the same because there's no hope with that. But I mean, can you associate with this a matrix that is going to be square and in fact symmetric? I'll give you a hint. Not only do I want it to be square, I want it to be n by n. So I give you an n by n, excuse me, an m by n matrix. I want you to prestidigitate for me an n by n matrix square that is also symmetric. That's in a natural way associated to A.
I don't think, well, this would make it symmetric, but you can multiply the identity in front to get n by n. Or I n in front, because then it would be a.
When you define in front, because here's the problem. If you take in and then multiply it in front, it doesn't multiply. But if you multiply it on the other side, it just gives you a back. Yeah.
I don't know how. Oh,
That's more.
I don't know how you do it, but just eliminate those 0 rows and 0 columns, or like for the examples you.
Right, but I mean, maybe it's something like this, right? I don't know, 1, 1, 2, 4, 1, 3. Right, and there's data in there that you might not want to throw out.
Could you multiply by a transpose?
There you go. What do I know about this trend, this matrix? Well, it's now this one is n by m, and this is n by n. So this is n r n by n, and it's symmetric. So it's symmetric. Oh, fantastic, right? So if you walk up to me on the street with A, all I have to do is go ATA, I'll have an M-by-N matrix and it'll be symmetric. And you know what? So let me ask you this. The eigenvalues are blank. What are they? True about the eigenvalues of any symmetric matrix. I think you guys really know this.
What about the information?
There we go.
They're real, right?
Okay.
But if it's of this form, ATA, it goes further. Not only they're real, they're not negative. They can be zero, they can be bigger than zero, but they can't be negative. This is not obvious, right? I mean, we had to go through a little bit to sort of half show that they're real. Why are they not negative? Well, this, I should probably demonstrate why this is true. Right, so. Since ATA is symmetric. And there is a basis of our entry. In fact, I want to scale it in mind. I want to scale it. I'll do that. Orthogonal basis of Rn. I'm going to call it V1, V2, up to Vn, consisting of eigenvectors. Because with any symmetric matrix, it's orthogonally diagonalizable. And so there's an orthogonal basis of Rn that consists of eigenvectors of this. And let's also suppose lambda I, the eigenvalue for Vi. Now, I want to do this computation here. Let me make clear. When I'm using ATA VI equals lambda VI. Everybody okay with that? So the square matrix ATA has VI as an eigenvector for the eigenvalue lambda I. Okay, so let me do this computation. I think I lost it. Okay, so what is the, now remember, a VI is a vector. So what's the square of this? It's just the dot product with itself, right? And what's the dot product with itself? It's AVI transpose AVI. Right? Now let me use my sorcery here on the transpose. This is VI transpose A transpose A VI. Right. I just turning all this garbage around. And what is this? Oh, this is just lambda VI, right? So this is VI transpose lambda I VI. Right? Or another way to put this, let me put this in less fancy terms. This is VI dotted with lambda I VI. And I can pull this lambda I in front. VI dotted with VI. Which is lambda I magnitude of VI squared. So. Here's what I got. That's kind of a brief summary of what we went through, right? So let me make an observation. This is positive because this is an eigenvector out of an orthonormal set. It's only got to be one. It can't be the zero vector. This piece is greater than or equal to zero, right? Because it's the square of something. The worst you're ever going to do is zero. This means that lambda I is greater than worst case scenario 0. Am I okay with that? So notice, by the way, this is in fact lambda I if well, since lambda I bigger than or equal to 0, we arrange lambda 1 less center equal to lambda 2 less center equal to and the singular values, so I'll leave you with the definition of what this is. Singular values they are the square root or sigma I, which is the square root of lambda I, eigenvalues. And they're going to, well, sort of like de facto eigenvalues for what we're going to look at next time. I'll tell you how the decomposition works next time and do some computations. Don't forget you got a quiz due Tuesday, and don't forget to do your assessments as well. So you can come see me right now. My office hours do end at 1 again today, unfortunately. But that's the problem. Just let me know.